Section 2.5, Complex Zeros in the Fundamental Theorem of Algebra. The fundamental theorem of algebra is that a polynomial function of degree n has n complex zeros, real and non-real. Some of these zeros may be repeated. So basically, before now we talked about that the degree means that there's that many possible real zeros. Now, what this theorem is saying is that that degree actually tells us exactly how many zeros there are if we take into account real and non-real answers. So a few things to make sure we all know is a complex number in standard form is of the form a plus bi. So that's where we're talking about imaginary numbers. I simply is talking about that we took the square root of a negative number. So I equals the square root of -1. If I did a problem and I got something like square root of -25, I would say, well, I know the square root of 25 is 5, and the square root of a negative number gives me I. Okay, so that's how the I works, is I took the square root of a negative number, so I pulled it out and made it an I. It's also important to know that I squared equals -1. So if I end up with a number like 5i squared, then that equals -5, because the I squared part of it is -1 times 5 gives me -5. So if I have a degree of 3, then it's possible that I only have one real zero, and then I could have two non-real zeros. Okay, or there could be other scenarios that we might have as well. And then real numbers, the reason it says complex zeros, real and non-real, is that technically if I have a number like 3, I can write that as a complex number because that would be 3 plus 0i. So complex numbers are all of the numbers, and then we can split that up into real and non-real. So before now we've just been talking about the real zeros. Now we're going to throw in the non-real zeros as well. The linear factorization theorem, I believe, is in the section before this, and it's just continuing to say, hey, if I know what the zeros are, then I can set them up as linear factors by changing the sign and putting them in parentheses. Like before, we worked problems where we said, I know x equals 3 and -1 and -5, so that meant that our linear factors are x minus 3, x plus 1, and x plus 5, and then we can find that polynomial if we want to. Well, now it's saying even if I have some non-real zeros, then that still is the case, and we'll see how to, in a later example, how to put those into parentheses. The fundamental polynomial connections in the complex case basically is saying that all of the things we know about normal zeros are true for complex zeros, or non-real zeros as well. That if x equals k is a solution or root of the equation f of x equals 0, then it's also considered a zero of the function, and then x minus k would be a factor. It doesn't matter if it's a non-real zero, it still works the same way. So example 1, this is similar to example 1 in the book, not the exact same numbers. Write the polynomial function in standard form, identify the zeros of the function and the x-intercepts of its graph. All right, so it gives us f of x equals x minus 3i times x plus 3i. Let's go ahead and FOIL that out and tell them what this would be as a polynomial. This is FOIL. X times x is x squared. Outer is x times 3i, which is 3ix. Inner is -3i times x, which is -3ix. And then last, this is -3i times positive 3i. Well, if I multiply that together, I get -9i squared. -9i squared is really a positive 9, because I squared is -1. So -9 times -1 gives me 9. Okay, well, because this was the difference of two squares, I actually can now cancel out my middle terms. 3ix minus 3ix is 0. So f of x equals x squared plus 9. That is the polynomial function that they wanted us to write. It asks us to identify the zeros of the function and the x-intercepts of its graph. Well, my zeros come from my linear factors here by changing the sign of each of those linear factors. So 3i and negative 3i are my zeros. Now let's think about our x-intercepts of this graph. This is a pretty easy graph to draw because it's a parabola that's shifted up 9. We'll pretend that's 9. Okay. So does that have any x-intercepts? No. It starts at 9 and then it goes up. So we can see that by looking at the zeros. I have imaginary zeros. I don't have any real zeros. If I had real zeros, those would be the x-intercepts. Since I don't, I would say no x-intercepts. Okay, but if we had some real zeros, those would be the x-intercepts. Complex conjugate zeros. Suppose that f of x is a polynomial function with real coefficients if a and b are real numbers where b does not equal 0, and they tell us a plus bi is a 0 of f of x, then its complex conjugate, a minus bi, is also a 0 of f of x. So in other words, if they tell us that, 3 plus 5i is a 0, even if they don't tell us this next part, we know that that means 3 minus 5i is also a 0 because they're complex conjugates. The complex conjugates have the same exact numbers, you just change the sign that's in front of I. So similarly, if they told us like 5i was a 0, then we would know that negative 5i is a 0 because that's like I have a plus 0 in front and a plus 0 in front, and I just change the sign that's in front of I. So for example 3, now we'll be able to actually work this out and figure out what this polynomial will be, because we have 3 zeros they told us, but we actually have 2 more, because if 3 minus I is a 0, then so is 3 plus I. If 2 plus 5i is a 0, then so is 2 minus 5i. Okay, so if I plug these in as linear factors, because I'm trying to write this as a polynomial, I'll have x plus 3, and then I'll have x minus 3 minus I, then x minus 3 plus I. I'm going to put the complex conjugates next to each other because if we multiply them together first, it makes it easier. Okay, now right off the bat, this probably looks like quite a bit of work, and it can be, depending on how you do it. There's kind of a trick to multiplying difference. Basically, what we have here, if I think about what I normally do whenever I FOIL, like let's take something easy real quick and talk about what I do whenever I FOIL. Is the first term is x squared, then plus 3x plus 1x plus 3, so that I get x squared plus 4x plus 3. All right, well, what did I do there? I said I have x squared. Okay, that's always going to be the case that we start off with x squared. My middle term is what I got when I added the two numbers 1 and 3 together, and then I put an x. Okay, and then my last number is what I get when I multiply the two numbers together. See how that works? Now, what we really have is where we're subtracting things. So maybe it would be better to look at if I subtract x, something like this, x minus 2 and x minus 3, and I FOIL that, I get x squared minus 2x minus 5x, and then plus 6. So that's x squared. I'm sorry, that should be 3x. I jumped ahead of myself. So that should be x squared minus 5x plus 6. All right, so what I did is I added my middle terms and then I multiplied them together. Okay, so they're keeping the sign that they have. Let's try to apply this now to what I have here. Okay, I'm going to say this is x squared And then I have these two numbers added together. Well, they're both negative, so that is minus. And then if I do 3 plus 3, that gives me 6. Negative I plus I gives me 0. So that my i's canceled out and I really have negative 6x. Okay, because I added 3 minus I and 3 plus I together. Now, if I do the last part where I multiply them together, a negative and a negative will give us a positive, and then I need to think about what 3 minus I times 3 plus I would be. Well, this is the difference of two squares. So I have 9, my outer and inner terms cancel out, and then I have minus I squared. Well, 9 minus I squared is really 9 plus 1, which is 10. Okay, so that's x squared minus 6x plus 10. Let me write my first factor back. Okay, let's do the same thing on this next one now. So hopefully that we can make sure we can get this. I'm going to start off with x squared because that's always what our first term is going to be. X times x is x squared. Then I'm adding together two negatives, so it'll be minus 2 plus 5i plus 2 minus 5i is 2 and 2 is 4. And then my i's cancel out. And then if I multiply together 2 plus 5i and 2 minus 5i, I get 4 for my first term. My outer and inner terms cancel out, and then I get negative 25i squared. Well, that's really 4 plus 25, which means this is plus 29. Now, this is still a long problem to finish, but that's a lot easier than if I had tried to distribute all of this. Okay, so this right here is our rule up at the top, that I do x squared first, then I put what is it if I add them together, what is it if I multiply them together. Okay, so I don't really know what the easiest way to do this is. Let's go ahead and multiply these two together and then multiply by x plus 3. So I'm going to distribute my x squared into my second or my third parentheses. So that's x to the 4th minus 4x cubed plus 29x squared. Now I'm going to do the negative 6, so that's negative 6x cubed plus 24x squared. 29 times 6, well, it'll be negative 174x, and then I'm ready for the 10. So plus 10x squared minus 40x plus 290. Let's add like terms. X to the 4th is by itself. My x cubes give me negative 10x cubed. My x squareds give me, that's 53 plus 10 is 63. Then my x's give me negative 214, and then plus 290. So now I need to take that and multiply it by x plus 3. So I'm distributing my x and then I'm distributing my 3. So x to the 5th minus 10x to the 4th plus 63x cubed minus 214x squared plus 290x. Now I'm distributing the 3 plus 3x to the 4th minus 10. Just kidding, minus 30, because I multiplied by 3. X cubed, 63 times 3 is 189. So plus 189x squared. 214 times 3 is 642. And then 290 times 3 is 870. So now once I add like terms here, I'm done. So this is f of x equals x to the 5th. My x to the 4th gives me negative 7x to the 4th my x cubes give me plus 33x cubed. This probably should be a squared. Negative 214x squared and 189x squared will be 25x squared. My x's give me 290 minus 642 is negative 352 x, and then plus 870. Now, I'm not promising that I did all that math right, but the basic gist of it is hopefully pretty clear on how we would multiply this out and get this as an answer. So that's kind of a long problem. Not all of them will be that long because we won't always be multiplying 5 things together, but that's how you do it if it is that long. I think that this is in the next video. I'm really gonna hope so. So part 2 coming soon.